Okay, we have studied the curve fitting and least squares, and we stopped where for the linear least squares. But in many cases, the curve fitting itself is an optimization problem, as you already know. But in many cases, it's not linear models. A lot of cases, nonlinear models. Assume that we have this example. We have n data points to fit a model fxia, where a is a set of parameters. We have the method of nonlinear least squares to minimize the L2 norm of the residuals. The residual itself is ii equal to yi minus fxia, to see that yi is the observation and fxia is the predicted function value from the f. So that is how we can define ii. That is to minimize the sum of the fit errors residuals. Squared actually, right here is it's not 100% accurate, but minimize the sum of the squares of the fit errors or residuals, sum of squares of the fit errors or residuals. So you're trying to minimize this EA error in terms of parameter A, and then sum of RIA squared. And each one of them can be represented this way. And then based on the definition of LP norm that we discussed earlier, this is essentially L2 norm. And the L2 norm, for this minimization problem, you can solve it use Gauss-Newton algorithm. So what you do is you use J, denote the Jacobian matrix in the form that each element Jij is partial derivative of Rj, Ii in terms of Aj. And I and J are the notation. So here you see that essentially it's the element index in the matrix. And this Jacobian matrix is n times n plus 1 matrix. And then you can also get the gradient of the objective function, that is partial derivative in terms of error term. We call it partial derivative E. In terms of Aj, it is 2 times partial derivative of Ii in terms of Aj times Ri, sum of them all. So you can see the relationship between the gradient of the objective function with a Jacobian matrix. So the gradient can be written in a vector form of gradient of E with n plus 1 components as gradient of EA equal to 2 times J transpose times R. So in other words, using the Jacobian matrix to represent the gradient that we just calculated, where the residual vector R is given by RA, I1A, R2A, etc., and the Hessian matrix H of size n plus 1 times n plus 1 of E can be written as the original Hessian matrix. Remember that it has diagonal elements and off-diagonal elements in terms of x1, x2, x1, x3, etc., for the Hessian matrix. And the Hessian matrix can be rewritten based on Jacobian matrix. It would be 2 times J transpose times J plus 2, and with this particular function form. And then roughly, Hessian matrix can be approximated by 2 times Jacobian matrix times J. That's why you see the similarity of the Jacobian matrix to the Hessian matrix that we discussed earlier. And the minimization of EA can be solved by Newton's method, starting with the initial guess of A0, which is similar to what we discussed earlier with the roots, right? Square of roots that we discussed. You can update next solution equal to current solution minus gradient of E divided by second order derivative of gradient of E, which is gradient of E squared. And then you can continue to simplify this relationship. You would find that AT plus 1 equal to AT minus a relationship, some sort of function with Jacobian matrix. This is Gauss-Newton method, which requires Jacobian matrix to be full rank. In other words, it can be inversed for JT times J. Inverse actually exists. And many software packages actually have implemented this method, Gauss-Newton algorithm. Then once you saw it's nonlinear least squares, you can leverage Gauss-Newton algorithm to solve it. Let's use it as an example. We use this data set to fit this model. Why is that? And then we're trying to find coefficient AB so that we can to fit that data, right? Objective is to minimize the sum of the residual squares, and then you use residual being that being that so here apparently there's a typo here as well. This is not 1, it should be yi. So yi minus y minus x divided by a plus bx squared. And then each ii is yi minus that. So this is really yi. And then once you have that, you can calculate partial order derivative in terms of A, partial order derivatives in terms of B, and then you use an initial guess of A equal to 1 and B equal to 1, and then you find the initial residuals, and then you can implement the algorithm to come back with our final solution of A and B. This is an exercise that you can work on your own using R or Python, but the algorithm itself is straightforward as what we discussed here. If we continue with this, right, you can find the initial Jacobian matrix, and then you can find the first iteration based on initial guess of 1, 1 minus Jacobian matrix inverse times J times R, and then you come back with the updated A and B, and then you can update that A and B by updating the new Jacobian residuals. We have A of this first iteration. The first iteration using AB gives this. And then we're updating the new Jacobian and residuals. We got a new AB after the second iteration. That's the second iteration A and B. And then third iteration is this, and the fourth iteration is this. And it converges very quickly. Parameter almost remain the same after 10 iterations. It's a very good exercise. You should do it yourself to get a sense and flavor of what this algorithm is. And then when you start using it, you're no longer running this on your own. It's more like calling the function directly. But at this point, I think it's worthwhile to do this on your own to write the algorithm yourself. Okay, let's look at another method that can be used for nonlinear least squares. It's called Levenberg-Marquardt algorithm. So also called LM algorithm. And let's say what that is you start, it's more robust by using a damping term in the approximation of the Hessian matrix. Its Hessian matrix is 2 times J transpose J plus mu I. This mu I term is really the new damping term that we referred here. This term. So original Gauss-Newton algorithm only have this term, doesn't have this term. Where mu larger than 0 is the damping coefficient, also called Marquardt parameter, and I is the identity matrix of the same size as H. Thus, the iteration formula becomes AT plus 1 equal to AT minus this side. That's our iteration formula. It is equivalent to the step size of ST in the line search given by this relationship. So mathematically speaking, a large mu will effectively reduce the step size in comparison with those in the Gauss-Newton algorithm and damps the moves with the right amount. If the reduction in E is sufficient, we can either keep the value of mu or reduce it. However, if the reduction in E is not sufficient, we can increase mu. So its idea is really that we could use the information that we got to revise mu so that we can converge a little bit faster. If mu equal to 0, this algorithm reduces to the standard Gauss-Newton algorithm. Since mu is not 0, this JT J plus mu I is always full rank, just because JT and J has to be full rank. If it's full rank, then JT times J plus mu I is always full rank. That's therefore it's invertible. Okay, so that's the LM algorithm. It's just a variation or another a more enhanced version of Gauss-Newton algorithm. Weighted least squares. In some cases, we have to use weighted least squares to solve an optimization problem, or or to solve a curve fitting problem. The methods so far implicitly assume that all data points have equal variance. If you study linear regression more rigorously, you would know that one of the assumptions for linear regression is equal variance. But here, what if the data points doesn't have equal variance sigma squared? To consider the possibility of different variances, sigma I squared, we have the weighted least square. So we use, instead of minimize the sum of Ri squared, we use Wi times Ri squared to be our error term, and then we're trying to minimize that weighted least squares. And then we can further reduce to this form, which is identical to what we discussed. Essentially, we use that weight being 1 over sigma I squared to be the weight, so that can be reduced to this form. Each weight is 1 over sigma I squared. And then it's an LP norm, L2 norm of II over sigma I. And we use this Wi equal to 1 over sigma I squared, and sigma I squared is a variance associated with data points of xi and yi in a certain xi value realization, or in a certain interval of xi's. If you would rather to group some of the xi's together, close by xi together, and then you would be able to come back with a variance of all the data points of xi, yi. So by defining a weight matrix of W as diagonal of all this Wi, smallized Wi, and then a smaller sized Wi, and then the following similar derivation as above steps increments will becomes a new matrix that is how to update a t plus 1 from AT based on the Jacobian matrix and the weight matrix. And the Hessian is 2 times JT transpose W times J, and the gradient is given by 2J transpose W and R. Now, this is the algorithm for weighted least squares that can help you to solve the problem that not all the data points have equal variance. Regularization. You probably would hear this term quite a bit in a lot of machine learning data mining. If you go to a lot of meetups, you would see that people use this quite frequently. But now let's take a look at what is regularization. Regularization is another approach to deal with overfitting. In case of multivariate cases with p components, z equal to z1 all the way to zp, we have the linear regression model of y equal to beta 0 plus beta 1 z1 plus beta 2 z2, etc., and then it can be rewritten as a matrix compact form as what I showed here, I highlighted there, where beta 0 is a bias while beta is a coefficient vector. The standard method of least squares is to minimize the residual sum of squares, which is this, and then that's just linear regression. For linear regression, what we're trying to do is minimize the residual sum of squares. However, you can have a new definition, new type of regression that considers regularization. For example, here we call it ridge regression. So the ridge regression uses a penalized RSS, residual sum of squares, in the form that the first component is identical, but you got the second component. The second component is lambda times beta j squared, sum them up. So you can see that beta j squared is all the different parameters that we're trying to estimate. Now we have this penalty term, and then each one of them is based upon beta I squared, and then with the lambda being the penalty coefficient. And then this is a L2 norm, can be rewritten as this particular form. And then the idea is we don't really want, as we know, if we increase different parameters, we would continue to improve our fit of the model. But the thing is, if we have a lambda, we're trying to penalize this so that we're trying to minimize that sum of squares. Meanwhile, we want to minimize the possibility of too many betas. We don't want to have too many betas, so that we drive some of the beta j's to 0, and as a result, our model is more compact. More compact meaning I only have 5 betas instead of 50. That's really the idea. And then this is called ridge regression. And then ridge regression itself has 2 different forms. Let's say next page, I'm assuming that we are going there. Yeah, hold on. Yes, ridge regression has 2 different forms. One of them is called Lasso, if you ever heard of it. Lasso regression is essentially essentially L1 norm in the no, my bad. So I'm saying that regularization has two forms. One is called ridge regression, which is L2 form. And the second type is called Lasso regression. Lasso regression is, instead of using L2 norm, it's L1 norm. So that the second term is L1 norm. So the second term is L1 norm, same idea, trying to drive all the beta to 0 and so that we can come back with a more compact form of the linear regression. And then it's subject to all the betas absolute value add up to less than or equal to a C parameter. It's predefined hyperparameter. Again, we discussed hyperparameter is something that you can adjust so that you can find the best fitted model. And just to be aware, beta 0 is not penalized. Only the betas that beta 1, beta 2, etc., etc. If you go back to the previous slide, you should be aware of that as well. This beta j is only from 1 to p, not beta 0 itself. And then there's a hybrid regularization which actually takes into consideration, combines ridge and lasso together. You have L1 norm and L2 norm in the objective function. Both of them are being used. These regularization methods have been implemented in many software packages. If you ever heard of ridge regression, ever heard of lasso regression, you would know they're just regularization of linear regression. Okay, these are the software that you can refer to and also references that you should pay attention. So R has LM being the linear regression model, and Python has two modules for regression stats models and scikit-learn. Both of them have linear regression models. Just in addition to that, the module scikit-learn, sklearn, is mainly for data mining and machine learning, which can do k-means clustering and basic clustering as well as various statistical analysis. We're going to discuss what is k-means clustering and other basic clustering algorithms as well, especially from the optimization perspective. Okay, I'll stop here for chapter 4. If you have any questions, feel free to reach out. Thank you.